Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video we are going to talk about the brute force Bayesian algorithm and the Bayes optimal classifier. So before we begin, let's talk about what is MAP. MAP means maximum a posteriori, um, and that means it involves calculating a conditional probability of observing the data given a model weighted by a prior probability or belief about the model. So it is all about this prior probability which you are given about the model before you begin your calculation. And then you're calculating the conditional probability. So it provides you with an alternate probability framework to maximum likelihood estimation for machine learning. Now let's see the brute force Bayesian algorithm. So to do that, let us first assume that the learner considers a finite hypothesis space H, in which the learner will try to learn some target concept C, which has X. X is the instance space corresponding to H, and this contains 0 and 1. So the two possible values of X are 0 and 1. And that's the concept that the learner is trying to learn. And there is a finite hypothesis space, which means we are not talking about just one null hypothesis and one alternate hypothesis. We are talking about a hypothesis space H that contains many different hypotheses. And the sequence of training examples are given here. So you can have X1. So we already know what is X. It is instance space. And along with X1, we have a target concept. Okay, so there is X1, T1, X2, T2, and so on up to XMTN. And here Xi is the instance of capital X, Ti is the target concept of Xi. And what do you know about Ti? Ti is equal to C of Xi. So when you specify the value of Xi to the target concept, the answer that you get in return is known as Ti. Now, without impacting the efficiency of the algorithm, we can assume that the sequence of instances of X, which are, all the values from X1 up to Xn is held fixed. And then the sequence of target values would become T equal to T1 up to Tm, which is quite obvious. Okay. Now you have to calculate the posterior probability of each hypothesis, small h and capital H, because there's not just one hypothesis. We are dealing with multiple hypotheses at the same time. So you have to calculate the posterior probability of each of these hypotheses, okay? And to do that, let's say that small h is the one that you're calculating the probability for, then it's going to be P of h given T, which is all the target values. And we know this formula very well from Bayes' theorem. So it's quite easy. You just invert T and H here and use H over here, put T down below, and that's what we do. And you can also identify the H map with the highest posterior probability. So the idea is that you have lots of hypotheses, but not all of them are going to be correct. So you have to identify which of them have the highest value of H map, which I told you about earlier. Okay, so to do that, you're going to use this formula, which is argmax H equal to H, where the probability P of H given T is the maximum. So you're just applying an argument called max. And for all values of small h, you will find the probability of that h given the target values, and you will see which one of them is the maximum. So if you find that, then you can say that these are the hypotheses that are most likely to be true. Now let us try to connect the concept of this learning problem with the problem of identifying the h map. So on the basis of the probability distribution of P of h and P of t given h, we can derive the prior knowledge of the learning task. Okay, so how do we do that? So there are a few assumptions that you need to make before you begin. The first assumption is that the training data or the target sequence T is noise-free. Okay, so that means there is no error in it, there is no discrepancy in it, which means that it is a direct function of x only, which means you just have to pass you use this formula and you get the value of t. Okay. The second assumption we are making is that the concept C lies within the hypothesis space capital H. Okay. So the concept C lies within the hypothesis space capital H. And the third assumption is that each hypothesis is equally probable and independent of each other. So if you have 10 hypotheses, all of them have equal chance of being true, and they are also not dependent on each other. So on the basis of that, on the basis of the third assumption that says each hypothesis has equal probability, equal chance of being true, and also because of assumption 2, right? We can say that these prior probabilities would sum up to 1 because everyone has an equal chance. It's like tossing a coin or rolling a dice. All probabilities have an equal chance, which means if you sum up all the prior probabilities of all these hypotheses, you will be getting a 1. So we can write that P of H is equal to 1 upon mod H, where all small h will lie within capital H. So now, what is this P of t given H? It is the probability of observing the target values Ti in the fixed set of instances xi up to xn. Okay, in the space where H holds true and describes the concept C correctly. And if you use the assumption 1, so there were 3 assumptions. If you use the first one, you can say that if T is consistent with H, then the probability of data capital T, given the hypothesis small h is 1. And if T is not consistent, then it is 0. So that's what we have summarized here. The value of P of T given H will be 1 if all values of Ti are consistent with the hypothesis that you're testing, and it is 0 if all values are not consistent. Okay, so this is our original Bayes theorem concept or the formula which we already know about. So now if you put all these concepts that we studied into the Bayes theorem formula, you can say that the value that was here, which was P of T given H, which would be 0 if H is inconsistent, we would be getting P of H given T also equal to 0. But if H is consistent with T, then we know the value is 1, which means we have here instead of 0, 1. And P of H, we know that probability of each hypothesis is 1 by H, the total number of hypotheses. Just like tossing a coin, there are two outcomes, and so probability of each of them is 1 by 2. Rolling a dice, 6 outcomes, probability of each is 1 by 6. So that's why P of H is 1 by capital H. And if you evaluate that, you're going to get 1 upon mod H into P of T. So these are the formulas to be used in brute force Bayesian algorithm. Okay, if we define a subset of hypothesis H, which is consistent with T as HD, then by using the total probability equation, we can get the following. So we know that out of capital H, not all hypotheses are consistent with the target values. So we have to identify the ones which are consistent and create a subset of H with all the consistent hypotheses, which will be added to HD. We will denote that as HD. And we can calculate the probability, okay, by this equation. So what are we doing? We are calculating probability of each and every H which is present in HD, which we just created. Okay, so it is P of T given HI into P of HI, and HI belongs to all the hypotheses present in HD. And of course, you can say that P of T given HI is going to be 1 into 1 by H, which we already saw from our previous equation we derived here, 1 upon H into PT. So we can evaluate it like this. And the other one, we are doing this 1 into 1 upon H because these are all the probable ones. But the ones that are not probable, which means all HI that do not belong to HD, for them, the probability will be 0. So it will be 0 into 1 by mod H. If you add the 2, obviously this term is going to be 0. So this is the only term left. Okay. And we know that probability of HD, all the values of HD, will sum up to 1. So that is HD upon H. So that's how you can calculate PT. So basically what we've just done is taken the formula of PT out. So we are just taking PT on that side and added P of H given T on this side. And then we can calculate the probability of T or the target values. Now, if you use Bayes' theorem, you can calculate, we already found the value of PT, which is HD upon H. Okay, and if you put that in the Bayes' theorem, you would be getting this answer, which is 1 upon mod HD. And with our set of assumptions about PH and P of T given H, we get the posterior probability P of H given T as this. So this is our posterior probability, that if H is consistent with T, we get 1 by HD and we get 0 otherwise. We saw this even before, right? So what does that mean? Here, HD is the number of hypotheses from the space H, which are consistent with the target data set T. And how would you interpret this particular evaluation? You can say that initially all the hypotheses have equal probability, right? Because we do not know which one is consistent and which one is inconsistent. But then as you introduce the training data and the posterior probability of inconsistent hypothesis, it will all turn 0. Okay, as you introduce your training data, the data with which your model has to be trained, as you introduce that, the posterior probability of all the inconsistent hypotheses will become 0, right? Posterior is the probability afterwards. So prior probability is all equal, but then when you have your training data introduced, then you'll realize that, okay, now the probability is of inconsistent hypothesis is going to be 0. And so the total probability becomes 1. And that probability is distributed equally among all the consistent hypotheses in the set. So that's what brute force Bayesian algorithm is all about. And under that condition, each consistent hypothesis is a MAP. What is MAP? Maximum A posteriori. And we know that maximum value, because if all probabilities are 1 by 6 for rolling the dice, then all of them are maximum, right? So all of them become MAP hypothesis with the given posterior probability, which is 1 upon HD. Now let's take a look at the Bayes optimal classifier, because this will form a basis for whatever we have to study in the next video. So let us assume that there are 3 hypotheses, H1, H2, and H3 in the hypothesis space H. Okay, and the posterior probability of each of them is given to you, which is 0.4, 0.3, and 0.3 respectively. Now there is a new instance X, which is classified as true by H1, but false by H2 and H3. So you are introducing some training data, and in that data, you're introducing a variable X, a new value X, and H1 classifies it as true, but H2 and H3, your other 2 hypotheses, they classify them as false. Okay. So the most probable classification of the new X can be obtained by combining the predictions of all hypotheses weighed by their corresponding posterior probabilities. Okay, so we know that each hypothesis is not equally likely. Okay, one is 0.4, the other 2 are 0.3. So we have to weigh in the opinion given by each of them by using their probabilities. So if you do that by denoting the possible classification of the new instance as Ci from the set C, the probability of Ci given T, which is the correct classification, will be this. Okay, this is not very hard to understand. We already saw this, okay, formula. And the optimal classification will be this, where we've just introduced a value called argmax. Okay, this is the Bayes optimal classifier. Because we have 3 hypotheses and all of them are not equally probable. We are given their posterior probabilities. So we have to find out whose opinion matters more. Okay. Now, what are the set of possible outcomes? So you can say this is the first outcome, that for H1, which is true, you can say that h1 given t is equal to 0.4, where h1 given of the value that the probability that this is false is 0, but the probability that this is true is 1, because that's what h1 is saying, it is true. H2 is saying that x is false. It classifies x as false. So that's why it will fall here as x given h2 equal to 1, and otherwise true value will be 0. And for h3, we can say with the probability 0.3 that false is 1, but true is 0. So what can be the probability? You can add them. So for the true value, we can say it only the hypothesis 1 is saying it is true. So that would be 0.4 alone. But there are two hypotheses saying classifying that as false. So that is equal to 0.6 because both of them added together are 0.3 plus 0.3. Okay. And so this is 0.6. So which opinion would you go with? You have to go with the opinion that is larger. You see, if you add these two, you get 1, but it is divided. 0.4 is true. 0.6 says it is false. So that means probability of the classification of x being false is higher. So that's why this is the final formula which we will apply, and we will say that x can be classified as false. So what does this method do? To conclude, this method maximizes the probability that the new instance is classified correctly when the available training data, hypothesis space, and the prior probabilities of hypothesis are known. So it is called the Bayes optimal classifier. So I hope you understood all this, and I'll be back with the next video. So keep watching, and thank you for watching this one.